So what we did last time, we looked at an EMF induced in a magnetic field when you just move a conductor. And you can figure that out using the right-hand rule. That if you have a charged particle in the conductor, you know where the fingers go, this is the field, and you figure out the velocity and the direction of the motion, and the palm is the direction of the force. So we figured that out last time. Get the equation formula for EMF, we did that. Magnetic flux and magnetic flux linkage, we're actually going to pick up from that. And then how you induce an EMF by a time-changing magnetic field, magnetic flux, and Faraday's law, and Lenz's law. It's Lenz's law, which will actually lend itself towards the idea of railguns and moving objects. And be able to solve electromagnetic induction problems. Well, we'll sort of tip our hat to them as they fly by. So magnetic flux linkage from last time, if you have a magnetic field going through a surface, it's the product of the magnetic field strength and the area times the angle between the direction of the field and sort of the perpendicular direction of the area. So this was kind of a poor man's picture of what the magnetic field would look like from one of these neodymium magnets. That you'd have like a north side and the flux lines would go up and around, and you'd have a very strong field very close to the magnet because, well, you have a lot of field lines there. But when you want to get the magnetic flux, if you had an area that you put in that would be, well, the field is going up, and if you put this in here with the perpendicular to the area in the same direction as the field, then you get a lot of magnetic flux linkage. But if you put it in perpendicular to that, then you get basically virtually no magnetic flux linkage because it's perpendicular, and none of these lines are going through here. And this is essentially how many lines of magnetic flux are going through an area. So that's what that is, and it's kind of a model for a neodymium magnet. And when you tilt this, you have this cosine angle. So if you go 90 degrees, that the flux lines are going this way, and your area is perpendicular, you'll get no flux. And we use this symbol phi as the magnetic flux. And the linkage is what actually goes through an area. And if you had several loops, you actually have, we talk about having the multiple copies, n times the magnetic flux linkage for just one loop. And the EMF that's generated here is actually the change in time, the rate of change of this magnetic flux linkage. And so if you have multiple loops, it would be n, and this is actually Faraday's law. And so we talked about that last time very briefly. And so this is Faraday's law. This is in your data booklets, by the way. One of the equations for that. Now, as part and parcel of that, there's Lenz's law. And Lenz's law, it's kind of conservation of energy. It says that if you have a change in magnetic flux going through an area, through a closed circuit, that circuit will try and generate a current to oppose that change in flux. So for instance, if we started bringing this, let's say this is the north end, and these loops are all going up and around, then what would happen if we brought this close to this, that we would have flux lines going through this area. Now that would mean that the current in here would act to oppose that. So the current in here would try and put a magnetic field pointing down. I have no idea what that is.
iPhone.
So, pardon me?
Was that the iPhone?
That was the iPhone. So that's pointing, so that would be pointing down. Does that make sense? Kind of? Okay, let me think of it another way. Trying to oppose the motion. Here's a picture of that. Let's say that here's a circuit, a current loop. It's just a wire in a circle. and we're bringing a north end of a magnet to it. And the lines of magnetic flux from a magnet are going to curl around and point to the south end. So when we bring this magnet close to this current loop, that means that the flux lines from the magnet will want to go through here, pointing in this direction. And what the current inside this loop here will want to do will be to oppose that. So for instance, suppose I had a bar magnet here. Yeah, I have a bar magnet here. And let's say this is the north end. And you bring it close to here. The magnetic field lines will want to point this way if they're going to curl around. So what direction would the current be in this loop so that it would oppose it? This is a right-hand rule question. Which way? Well, I mean, let's say the magnetic field from here, the magnetic field lines are going to point this way. But this thing will want to oppose it, so it will have the magnetic field lines trying to oppose it. And then if you use your right-hand rule, that means that the current in here is going to go along the lines of your fingers. So it's actually going to go in this way. So it's going to go up towards you and down towards me. Okay? And that's the kind of thing that IB will ask for. What direction is the current flow to try and oppose a magnetic field. And you need to remember that the magnetic field goes from like north to south outside a magnet. So for instance, so if you brought this magnet close to this loop, well, basically the same thing. You try and oppose it. So here is something that is metal. It's basically a current loop. You think of it as an extended current loop, and this is a magnet. So this is going to try and generate a current inside the copper to try and oppose the magnetic field. So if you drop this in, I mean, if you drop it just normally, it falls through. But if you drop it through here, so that's what's going on there is that it's basically the copper tube below this is trying to generate a magnetic field that goes in the opposite direction and opposes it, so it's pushing down. And then the copper tube above it is trying to create a magnetic field to keep the field strength high, so it's going to create another opposite magnetic field that's going to try and pull it up. So the end result is that this thing just takes a long time to drop through. Whoa! Back in. Yeah. Now, that will work for something over through here, and here, you can pass that around. Another application